Right, so there's a couple of things I want to try and get through this morning. I guess the best place to start off is where we finished off yesterday. So we were talking about the internal storage that happens within a Git repository. Apologies now for the drilling that's going on in the background, but I can't control that. So what we discovered was that everything inside a Git repository is called an object, and there are three types of objects: blob objects, tree objects, and commit objects. A blob corresponds to a file in your project, a tree corresponds to a directory, and a commit is an object that's created when you perform the git commit command, essentially. And then we said, well, what happens when you do a staging? And we said that when you stage, all of the files that are being staged, they're actually put into the repository at that stage. In other words, that involves Git looking at the contents of the file, computing a hash value based on that content, and it uses that hash value to determine the name of the object file that's going to be put into the repository. Those blob objects, though they're not connected in any way to the rest of the repository, if you like. They're kind of standalone. It's not only when you do a commit that it essentially brings in the directories involved and hooks them all up into the network. Essentially, Git maintains a network of these objects within the repository, and I'll try and explain that as well this morning. So what we did yesterday was, if I go over to VS Code, we had this simple project, if you remember, which had two subdirectories, dir A and dir B, a file within each of those subdirectories, and we also had a git ignore file. And we staged and committed that to the repository. So all that's in our repository right now is, if I do a git log, is one commit. And if we look at so this commit that it's showing us here, there is an object, a commit object within the repository behind that. And this is the hash value of that particular commit object. And we said, well, if we do a git cat file on that, we can see the contents of that commit object, if you remember. So if I copy that and I do a git cat file on that commit object, then it's giving us the same information as up here, but here's the important bit. It's actually pointing at, the commit object is essentially pointing at a tree object, and a tree object represents a directory. Now the tree object in this case is what I'm calling the base directory of your project, which, if we look up at the top left here, that's essentially corresponding to the demo folder, which is my base folder. And that should mean that if I do, here's the hash value, that's the hash value of that tree object. And so if I do a git cat file on that, in other words, show me the contents of the file corresponding to this hash value, this object hash value, because it is going to be a physical file in the repository. At the end of the day, the file's name is going to be based on the hash value that was computed for that, which I explained yesterday. But if I do a git cat file on this tree object, hopefully it'll tell me that there's a dir A and a dir B trees, and there's a git ignore blob object. And that looks like it's what it's telling me. So if you like, this here is referring to a file, and the contents of the file it's referring to is what I'm showing you here. And inside this file, inside in this tree object file, it's telling us something about what's contained within that tree, i.e. what's contained within that directory. And of course, we can confirm that that makes sense because there's a git ignore file in that directory in my working area. There's a dir A, and what's dir A? Dir A is a tree, i.e. it's a subdirectory. And similarly for dir B is also a tree. And finally, then, if I just look at one of those tree objects and do a git cat file on that, git cat file is my way of looking inside the contents of a particular object in the repository, whether that object be a tree object or a blob object or a commit object. So we've only looked at commit objects and tree objects so far, but if I do, and that now is actually what it's showing me here is the contents of, sorry, that's not what I wanted. Do that again now. That's not what I expected. Am I picking the right one? Just bear with me for a second. Oh yeah, sorry, yeah. Okay, when I looked at this guy, sorry, this one, I'm essentially looking inside the dir A, and it's telling me that inside dir A there is only one other object being referred to. That object's hash is this. And what type of object is it? It's a blob. And the name of the file out on your working directory is called file A. And if I did a git cat file on that, then finally I get to the contents of an actual file. So I'm just navigating through. What I'm doing there is I'm navigating through a network of objects, and eventually I'm getting to a blob object, and that does correspond to the contents of file A, isn't it? If I look at file A, yeah, that matches up. Okay, let's supposing I do an edit. If I make an edit to file B, I'll just call it first edit. Save that. And just before I do the staging committing, if we look back up here, so this is the first commit object in my repository, and it has a tree entry, and it has some metadata about the commit itself, who did it, when it was done, and the commit message. Okay, so that's fine. Now, if I do a staging and committing at this stage, so only staging one file, and I'm committing. Meaningless commit message, do my commit. Now there's another commit object. There's another blob object gone into the repository, which is going to correspond to the edited version of file B. And there's a new commit object, and there are some new tree objects as well. But if I look at the new commit, so if I just do a git log, clear this first. If I do a git log, just 1 second now. So I've done my git log. Here's the hash value of the new commit. So if I grab that and do a git cat file on that, the only thing that's different about this commit object is it has a parent entry here. And the parent entry refers to the previous, its immediately preceding commit. So the very first commit doesn't have a parent, obviously, but all other commits subsequent to that will have one parent. Some may actually have two, but for now, it looks like one parent. So that's so by having this parent entry, that's how Git keeps track of the sequence of commits, if you like, that that you performed on the repository. And it's the same story kind of as before. It has a reference to a tree object. And if we kept navigating around down through our network, we would eventually get to see what was the state of my working directory when I did this commit. And as we navigated through the network of objects, some of the objects that we would be looking at were objects that were created from the previous commit because they haven't changed. So, for example, we would be referring back to file A's previous blob object. There wouldn't be a new blob object for file A because it hasn't changed. Equally, for dir A, there wouldn't be a new tree object for dir A because that hasn't changed. There would be a new tree object for dir B because it has changed as a result of file B changing. Now, just to try and reinforce what the point I'm making there at the very end. So if I switch over to, this is part lecture, part lab now, but if I switch over to Moodle and if we go into the lab exercises, and there's some new lab exercises related to version control, but I want to look at the one at the very bottom. If I clicked on that, then you would get access to a set of PowerPoint slides, and I'll bring them up here rather than you having to look at them. Okay, so let's see what the exercise is all about. So I'm just giving you a particular context for this little exercise. So let's supposing I've got this project Maria, and here's my base folder. I have a dir A, and it has two files within it, file 2 and file 3. There's also a file 1, which is contained within base, if you like. So base contains a directory and a file, and there are two files within the subdirectory dir1. So that's my project, Maria. So let's supposing I do a staging and commit, my initial commit of that working directory. Then what I'm trying to show here is it's just my way of representing the internals of the Git repository in terms of objects and how objects refer to other objects. So I've just decided arbitrarily a diamond is going to represent a commit object, a box is going to represent a tree object, and a circle is going to represent a blob object. So if having done the initial commit of my project from the previous slide, then this is the set of objects that are going to be inside my repository. There's going to be a commit object. It's going to refer to a tree object. We tend to use the term root as being the very first tree object that's referred to by a commit. It'll always be a tree object. So that root, what I'm calling the root object for this commit, that really corresponds to your base directory. Okay, this guy. And if we looked inside that tree object, we would see, if we did a git cat file on it, we would see it would refer to a blob object, and the blob object is essentially related to file 1. It would also have a reference to another tree object. That tree object corresponds to my dir2. And if I looked inside the contents of this tree object, it would refer to two blob objects corresponding to file 2 and file 3. Okay, so this is my way of representing the network, what I'm calling the network of objects that are inside in my repository right now. Let's supposing we do this. We add a new file called file 4 to the base directory. So it now has a file 1 and file 4. And we do an edit of file 3 inside the dir2 directory. So we make those changes out in our working directory, and we also add a new file 5 as well to dir2. So they're the edits that we've done. We've added some files and we've modified some files. So we have a mixture of modified and untracked files. And I do a git stage and a git commit. Now my network is getting a bit more complicated. So this is the commit corresponding to this new commit that I've just done. It's going to have a reference to its parent commit. And it's going to have a reference to a tree object. And this tree object, again, corresponds to the base directory of our project when we did this commit. This tree object, it's actually going to have a reference to the blob object that was created from the first commit, because that file 1 has not changed. So it'll just have a reference to the same hash value that this one was referring to, because that file hasn't changed. However, it's going to have a reference to a new tree object, and I'm just labeling this dir2, sorry. I'm labeling this dir2 subscript 2 just as a way of letting us know that this tree object here corresponds to dir2 in my project, but it's a new version of dir2, if you like. It's different from the version of dir2 that's over here. This tree object is going to refer to the original file 2 blob object, because that has not changed. However, it's going to refer to a new blob object And this new blob object is the edited version of file 3, because I said on the previous slide, I made some changes to file 3. So we now have two blob objects related to file 3. We've got this one and this one. However, this is referring to the most up-to-date one, and we're also referring to a new file 5, because that was created. Also over here, we said on the previous slide that we created a new file 4, and that new file 4 was in our base directory. So this tree object is going to refer to a new blob object representing file 4. So if you like, I talked about every time you do a commit, what Git does is it takes a snapshot of your working directory at that point in time. And this is a snapshot. I won't draw all the way around it now, but sometimes the snapshot refers to old stuff, which it does in this case. And sometimes it refers to new stuff, which it does, like in terms of here. However, here it's referring to something that's old, if you like, and so on and so forth. But it is a snapshot. So for each snapshot, it'll either be referring to new tree or blob objects, as in here and here, or it'll be referring to old tree or blob objects, as it is here. There is no old tree object in this case. And kind of on and on we go. Let's suppose we do another set of changes. Edit file 1, which is up in our base directory, and we add a new subdirectory to dir3. Sorry, dir3 is a completely new directory, and we have a subdirectory within that and a file within that. Then we do a staging and a committing, and it starts to get even more complicated. So this is our new commit, and I won't talk my way through this, but if you just follow the arrows, there's always going to be a new tree object for your corresponding to your base folder. And we tend to refer to that tree object as the root tree of a particular commit. And if you follow the arrows, you know, some of the entries in this root tree object refers to earlier blob or tree objects. So for example, if you follow this line here, it's referring to this tree object because we haven't made any changes to dir2. If I just go back, there's no references to dir2 here, so we haven't made any changes to dir2 whenever dir2 was last modified, and it was modified in the second commit, and so on. Okay, it does get complicated, but that's Git kind of takes care of all of that for you in a way. And this again is another snapshot of the working directory at a particular point in time. If you follow all the lines, some of them drift over here, some of them don't. So that's actually what how Git works behind the scenes when you do a staging and committing. By the way, when you do a staging, for example, you know, this, if we just take this file here, okay. When we do a staging, the new or modified files are added to the repository as blob objects. So that blob object would be added to the repository, but it wouldn't be connected up to any root. Similarly, this is probably a better example. This is a completely new file. A blob object corresponding to that file would be put into the repository, but it would not be connected to any tree objects. It's only when you do the commit that these tree objects are brought into the picture. If you look back at the slides, that's what I was saying, but okay, where's all this going? If you just take a next, let's say, I'll give you about maybe 5 or more minutes, maybe. let's supposing we decide these are the changes that we now make to our repository. Or sorry, these are the changes we make to our working directory, and we stage and commit them. And the challenge I'm setting to you is, can you, and by the way, like, you know, I've ignored C1 here, the first commit. I've left a lot of C2 here just for illustration purposes. But once you start adding on more commits here, you know, you need only refer back to particular trees or blobs from earlier commits. You don't have to draw the entire lot. So what I'm kind of challenging you is start off here with a new commit object called C4. Sorry, no. Do that again. Sorry, where was I? Yeah, this is going to be C4. And see, can you complete the drawing based on this set of changes that were made in the working directory and staged and committed? So I'm going to set that as an exercise for you right now. I don't know if you've got any kind of pen and paper in front of you, but let's see, by my watch, it's, so if I give about maybe 5 minutes to see if you can whip something together, and I'll resume. I'll show you the, let's see how we do this now. Maybe it wouldn't really work now if I just say, I'll stop talking for 5 minutes, maybe. I'm going to let that as an exercise for you to do, and I'll put up the solution at the end of this 3-hour session. Maybe if I do it that way, I'm going to continue on lecturing. And when I give you the solution to that, then have a go at this. Now, for scenario two is also going to be our C4. So this scenario is a follow-on from here. You know, you're not going to have a C4 and a C5. C4 is either going to be this on the left or this on the right. My first challenge is do the one on the left, and then I'll show you the solution at the end of this 3-hour session. And when you see that solution, then have a go at, say, this one. And again, this one now is a continuation of here, like so. It's going to be C4 again. Just two alternatives. If we were physically in class, then I would split into 2 groups, and I would say one group take this one, another group take this one. Okay, so I'm just going to let it hang there, and when I've finished lecturing, you can have a look at this one first, and then later on today or tomorrow, have a look at this one, and I'll put the solution for this one up maybe tomorrow or the day after. Right, so you can get these slides, you can get them on Moodle. Where did I find them? I got them here behind this one, and you can do that later on. Okay, the next topic I want to look at is branching. So there should be a set of slides on Moodle, I think, on branching. Yeah, so you can get the slides. Sorry, now. You can get the slides here. But we have, just before I move off from it, we have this sense now of our network of objects within the repository. And I've used that term, a snapshot. A snapshot is a kind of a freezing of your working directory at a particular point in time. Each commit is a snapshot of your working directory at a particular point in time. Some parts of that snapshot are new root and blob objects, new tree and blob objects. Other parts of that snapshot refer back to tree and or blob objects that were created from a previous commit, not necessarily the immediate preceding commit. It could be one further down the line, further downstream. There isn't any case here, I don't think, but well, file one. Yeah, there isn't actually an example here, but I mean, it's possible that C3, this commit somewhere within this network, it would be referring to either a blob or a tree that was created way, way back in our initial commit, because we just never made any changes to that directory or file. Okay, let's leave it at that. And I'm just going to start talking about branching next. So if you go into Moodle and go into the version control section, there's a branching link there, and that will give you access to a set of slides. And these are the slides. Just bear with me. Okay. So we're talking about this concept of our practice of branching in version control, but in Git in particular. And so what is a branch? I'm saying a branch is when you want to diverge away from the main line of development. And why would you want to do that? Well, if you want to do any one of these tasks here, you want to start developing a new feature, you're in the middle of a project, you want to start developing a new feature, then you should do that development work on a new branch. When you create a repository, initially, there is always one branch there as part of the repository called the master branch. That always exists, but you can create other branches. And so if you're doing any one of these tasks here, developing a new feature, refactoring some existing code, debugging some code, or even just doing some exploratory work, you should do that work on a branch other than the master branch. It's considered bad practice to do it on the master branch. You can, technically you can, but it's just bad practice. So pretty much any type of development work that you're doing, you should be doing that development work on a branch separate from the master branch. And when you've completed that development work, you can certainly bring that into the master branch. And that's what we call merging two branches together. And Git will do that for you. There's a command to do that. If it can, it will do the merging for you. So that's fine. So whereas in last week's lab, we were doing some development work, but we were doing it all, we were committing the work onto the master branch every time. Okay, we didn't use that terminology then, but that's what we were doing. Every time we did a Git commit, we were committing, we would say we were committing to the master branch. Whereas now I'm suggesting that the workflow we should follow is this branch edit merge workflow. And what that means is just when you're about to embark on any one of these tasks here, the very first thing you should do is create a new branch. Then do your development work on that branch. So you do your editing of your files, creating files, staging and committing on that new branch. And then when you've completed whatever your task you're working on, then you can merge that new branch back into the master branch. Having done the merge, you've now completed some task and you're going to start your next task. Again, your next task is going to be one of these here, more than likely. What's the first thing you should do? Create another branch. Do your development work on that branch, staging and committing to that branch, and then merge that branch back into the master again. And on it goes. So this branch edit merge workflow, that is the correct workflow that anybody should be following when they're using Git as their version control tool behind the scenes. Really, you shouldn't ever be performing a Git commit when you straight on to the master branch. You can, technically you can, and Git isn't going to complain about it, but it's just considered bad practice. Now, earlier on, we were talking about all of these objects in our repository. And so in this diagram here, I'm just representing that information again. So my green boxes now are my commit objects. And we know from earlier on this morning that each commit object refers to its parent commit, and also a commit refers to a whole network of tree and blob objects. And I'm referring to that as being a snapshot of the repository at a particular point in time. That's fine. We had all of that this morning. What's a branch then? How is a branch kind of physically represented within the repository? And it turns out to be much simpler construct, really. A branch is represented as a file, okay, but the contents of that file is just one line, and it will be the hash value of one of the commit objects in your repository. In fact, it will be, the most recent commit that you've done. So when you do a commit, we know from this morning, when you perform the commit operation, a new one of these green boxes is created, and the branch file, the branch that you're currently on, that file is just going to refer to the hash value of that new commit object. If you do some more development, another commit, a new commit object is created, and the branch that you're currently working on, the file corresponding to that branch, is just going to have its hash value changed. So it's a very simple, I'm saying a branch is a simple movable pointer to commit objects. So it's pretty standard in that sense. Okay, so this is just my way now of representing a branch in terms of my pictures. Okay, it's going to be a physical file, and we'll look at the file in a moment. But a branch is just a file that contains a reference to a commit object, simple as. And if you're not going to be creating any branches, then as we know, by default, there is a branch called the master branch. So there is going to be one of these branch files in every repository initially, and that file is going to be called master. And if you never create any new branches, every time you do a commit, that master branch file is just going to be always referring to the most recent commit object that you just created. In other words, it's just going to have the hash value of the commit object. So when we do type the git status command in the command line, and we get back this is the response you're saying you're on branch master. Well, that's how Git knows which branch file it should update when you do a commit, because it knows it's telling you here you're on the master branch. So clearly, if I do a git commit down here, then it's the branch file corresponding to the master branch file. That's the one that's going to be modified. So that's how, if you've got multiple branches in your repository, how does Git know when you do a commit? How does it know which branch file it should update, which branch pointer it should update? Well, it's whatever it knows to be the current branch, if you like. And we'll see in a moment how it knows what the current branch is. By the current branch, I mean the branch that your working directory is aligned to. So this is how Git knows the correct branch pointer to move when you do a commit. And if we look inside the repository again, in this case, if we look inside the refs folder, and the refs folder will have a subfolder called heads. And inside in the heads folder, there will be a file for every branch associated with the repository. Initially, there's going to be a file called master. And if we looked inside that file, and I'm showing you here on the left, it's going to have something like this, okay? It's just going to have the hash value of the last commit that you did in this repository. I know there's a folder up here called branches, but I think that's actually redundant now. It doesn't use that anymore. It's all happening down here in the refs folder. That's where all the branching stuff goes on. So what am I saying? File is a simple text file containing the hash value. That's fine. And yeah, okay, that's if you just wanted to actually navigate into the repository, that's how you get to it. Okay, so how do I create a branch? Surprise, surprise, there's a command called git branch, and you just go git branch and the name of the branch. Now, what that will do is it'll create a new file in that, where was it? In the refs heads folder, inside in the heads folder, we create a new file. The name of the file, in this case, the name of the file will be, human readable. It won't be a hash value. It'll be whatever name you used here for your new branch. And initially, that new branch file, it will have the hash value of the last commit that you did on whatever branch you're currently working on. When you create a new branch, you're not changing the branch that you're working on yet. You're just creating the branch. You're still aligned with some other branch. Let's say it's just the master for sake of argument. So both the master branch and this new experiment branch, both of those branch files will be referring to the same commit object initially, which was the last commit that you did. And that's what I'm saying here. And creating a new branch doesn't have any impact on your working directory. That's fine. So kind of visually now we can have this, we've got two branch files now referring to the same commit object. That's fine initially. I'm just going through a scenario here. So if I type git status and I'm getting back from it, you're on the master branch. By being on the master branch, we kind of mean that your working directory is aligned with the master branch. It also means if I do a git commit, then it's the master branch's it's the master branch file that's going to be updated in the repository. Okay, but anyway, we're on the master branch, that's fine. And when cat is a command, it's a Mac command, but what I'm trying to do here is I want to display the contents of a particular file, text file, and I'm navigating into my Git repository, going into the refs folder and the heads folder, and I'm asking it to show me the contents of this file as a text file, and I get back a hash value. Then I go away and create a branch, and I do the same thing here. I want to see what is the contents of this new branch file. And if you look, it's going to have the same commit value that I got up here. And that kind of confirms that initially, when you create a new branch, it's just going to refer to the last commit that was made on whatever is the current branch. The current branch in our case is the master branch. If I do a git status again, I'm still on the master branch. So that again proves that nothing has changed from the working directory's point of view. Okay. Enter another file called the head pointer file. So this is a file. Okay, it's not it's a physical file. It's a standalone file. And the head file, I'm saying it's a special git pointer file, and it stores the current branch name that's aligned with the working directory. So really, when you type the git status command, if I go back to the previous slide, when we type git status, what git actually does is it goes and finds this new file called the head file, and it looks in there to work out, to determine what is the current branch that I'm aligned with. Okay. And so we've got this new pointer now, but this is pointing at a particular branch file. It'll actually contain the path name of the branch file, won't contain a hash value. Okay, so this guy is also a kind of a moving target. Every time you change branches, this changes, although we don't know how to change branches yet. Okay, so we've got this head pointer file, and I'm saying it's used by git status. Yes, it is. So when you type the git status command, the first thing that git does is goes looking for this file in the repository, and it knows where to find it. That file will just refer to the path name of some branch file. It looks like it's going to be the master branch file. And that's how Git can come back and say something like, you're on branch master. That's how it works it out. Sorry now for jumping back and forward in the slides, but scenario, git status on branch master. And if I do a git cat file on, if I beg your pardon, if I just do a cat operation, as I said, cat is just an ordinary Mac command for display the contents of a file. Don't know what the equivalent is in Windows. But I'm asking it to display the contents of a file called head, which is just inside my Git repository. And this is what we'll get back, something like this. It just refers to the path name of one of my branch files. And so that's what Git looks at when you do a git status. That's how it knows what branch you're currently you're aligned with. So there's a lot of things that we're juggling here. We're juggling branch files and this head file. There's only two things really, these branch files and this special head file. And again, if I just go back to, sorry now, keep going back. If we look here, here's the head file. Okay, so that's there from day one. That's always going to be there. Okay, now eventually we kind of get to, we want to go creating branches and switching from one branch to another branch and merging branches together. That's what I want to try and achieve in the next couple of slides. And so I'm setting the scene here, supposing that the current status of a repository, and so this is my way of representing, I hope it works for you. This is my way of representing the internals of a repository. So it looks like a C here corresponds to a commit. So I've done 3 commits. We don't need to look at the network of objects in this case now. 3 commits, and the master branch file is pointing at this commit, and head is pointing at the master branch file. Okay. Then we are saying, suppose we want to do some exploratory work, committed, but without interfering with the master branch. So what should we do? We should create a new branch and do our exploratory work on that new branch. So this is what we should do. Create the new branch. Just going to give it that as its name. This git checkout command, that's how you switch from one branch to another. Now, what do I mean by switching from one branch to another? Well, in terms of Git, it will change the head pointer to point to a different branch file. And also, it will align our working directory with that branch that you're changing to. And by aligning to a different, aligning the working directory to a different branch, it means that when we do a git commit we're now going to be committing to the new branch that we've aligned with. So git checkout experiment switches my focus from away from whatever the current branch is, let's assume it's the master, and switches our focus onto this new branch. And git equally switches its focus. So I've done this. I then make some changes in my working directory, do some ordinary edits and updates. In other words, I do my exploratory work that I want to carry out, and I do some staging and committing. I do a commit of that work, that's fine. Now, if we look at a snapshot, or sorry, if we look at kind of the internals of our repository, it's now going to look like this. So I've done a new commit. The experiment branch is going to be pointing at that new commit. Head is going to be pointing at experiment. Master is still going to be pointing at the earlier commit that it was pointing to. So the git branch command that created this guy here. The git checkout command changed head to now to be pointing to this, because on the previous slide, head was actually pointing at master. And then I did some development work in my working directory, and I committed it. And the commit created this new commit object. Experiment, which was pointing at this one, experiment is now going to be pointing at this one. Head hasn't changed, it's still pointing at this. So what we would now say is that we are committing to this experiment branch. We never say in a commit, what branch we don't have that freedom. You're always committing to whatever is the current branch. And whatever the current branch is determined by what head is pointing at. Okay, so yeah, that's fine. So this checkout command is how you switch from one branch to another. What happens when you submit this git checkout command? It changes head, as I've already said. Now, what it actually also does is this: it overwrites. Sorry. Now let's go back. I don't know why that jumped. When you do the git checkout, it does actually overwrite the working directory, and it overwrites it with the snapshot associated with the branch that you're switching to. And I put a warning signal here, right? But that doesn't mean that you could potentially lose some edits, because I'll explain in a while. It won't corrupt it won't cause you to lose some changes that you might have made in the working directory if you do a switch and you haven't saved or committed some modifications that you are making to the working directory. But it does anyway, technically, like it does overwrite the working directory based on the commit that's associated with the branch that you're switching to. Okay, there's a shorthand version of this git checkout command. If you use the -b option, that does two things. It creates the new branch and it switches to that. When we just use the git branch command, that just creates the branch. It doesn't switch to it. But this git checkout -b option has the effect of creating the branch and then switching to it. Back to our kind of scenario. So I do a git checkout of master. That's fine. I switch to master. I create a new, just the git branch command on its own, if you don't specify anything after it. What that does is it will list the current branches in your repository, and it's telling me that there are two branches. The asterisk will always be beside the one that's current. Now in VS Code, if I just switch over to VS Code, as you may have noticed, down on the bottom left of VS Code, way down here, is where, I don't know if that comes up on your screen now or not, just bear with me for a sec. way down here is where you will find out what is my current branch. And it happens to be master in this case. But the git branch command on its own will do that for you. It'll list all the branches and it'll put an asterisk behind the current one. So that's fine. If I then do a git checkout -b of branch X, so that says create a new branch called branch X and switch to that branch. I then do some edits to, let's say, file A and file B, and I stage and commit. If I now switch back to the master, when I look at file A and file B, I won't see the edits that I made up here. And that kind of confirms this point that I'm making, that when you switch from one branch to another one, the working directory is overwritten by the branch that you're switching to, whatever its status is. So I switched back to master here. And so the edits that I made here, which I committed to the branch X, they're not going to be visible now in my working directory. I haven't lost them. I can just switch back to the branch X again, and my working directory will now contain these edits. But anyway, so I go git checkout master, and I'm saying in the working directory, file A and file B are overwritten with whatever they were before I made these edits up here, I guess. And you could play with that yourselves, and you will in one of the labs that I've set up for you. Now, the point down here though is, if you're kind of follow with me, supposing I did this, I then did my edits, but I didn't commit them. I didn't stage and commit them. I just edited some files in my working directory. And then I tried to switch back to the master. Okay, Git won't allow me to switch back to the master in this case, because it'll know you have files in your working directory that have been modified, or maybe you've even added some new files, and you haven't staged and committed them to the repository under any branch. So it just won't allow you to do it. So you're never in danger of losing stuff when you switch from one branch to another. Okay, the next topic is diverging branches. What do I mean by that? So let's paint this scenario. So after committing changes to the experiment branch, we then check out the master, modify some files, and commit those modifications. So based on the way I'm trying to represent this now, my experiment was down here pointing at this commit. Then I switched back to the master. So head is now pointing at master. I modified some files, staged and committed them. Here's my commit. So effectively now, this branch here and this branch here, we would refer to them as diverging branches. They're going in their own direction. Okay, they have a common ancestor, which is significant. They're both linked back to commit 3, but from a other than that, you know, it's possible that changes that you're making to files here could well conflict with changes that you're making to files here. But for now, anyway, we just refer to these two branches as being diverging branches. And that's a very common thing in when you're working with Git. The two branches are diverging, but they have a common ancestor. That's fine. Now, eventually, you know, any work that you carry out in the branch, and I mentioned this at the beginning, work that you carry out on a branch other than the master branch, typically you want to merge that work back into the master branch, because the master branch should always have all of the work that you want to be part of the application that you're developing when you deliver it to the customer or deploy it for use by end users. So given that we tend to want to merge our branches back into the master, let's take a particular scenario. So I'm saying, supposing a customer has asked, could you develop a new feature for a particular application? Let's supposing this is a web application that's available to lots of customers, and some customer has recommended a new feature, and we think it's a good idea to develop that feature. So from a Git management point of view, we know now that we should develop this new feature on a branch away from the master, and then eventually merge it back into the master. So we've gotten rid of the experiment part of this now. So we've got our master branch, and we've created a new branch called Feature X, and we're doing some development work on that. I'm also saying over here that let's assume that the master branch, that version of this application, this fictitious application, the master branch is what is deployed, and that's what customers are using. And so that always has to be kind of squeaky clean. There can't be any bugs in that, obviously. But that's we're assuming that the master branch is always the version of the web application that is currently available to our end users. And that's why we're doing our development of this new feature on a different branch, so that we don't impact customers until we want to make that new feature available. Okay, so that's the status of this repository that we have now. However, let's say this arises while you're working on this new feature, somebody else reports a bug in the deployed version of the application, and straight away, obviously, we need to fix that bug and get the fix out onto the master branch as quickly as possible. But we will do the debugging on a new branch. And so we've got another branch now, which I've just called bug Y, and that's where we're doing our debugging. This may still be continuing on if we've got enough team members to divide up. So eventually, I guess we want to merge this bug Y branch back into the master to make it available to our end users. So my repository is starting to span out now, but technically the master and bug Y are diverging branches, and certainly feature X is diverging away from bug Y and master. So we've got 3 branches, and they're all going their own path. Like if I did another commit to master, then that commit is going to be here, and it's on its separate path. The bug fix is now completed, and it must be merged back into the master. How do we do that? This is how we do a merge. There's 2 steps to it. You first of all have to switch your working directory, switch it to the branch that you want to merge into. We're always merging into the master. So we check out the master, and then here's the merge command, git merge, and you specify the branch that you want to merge. You're always merging into the current branch. The current branch is master in this case, because we've just checked out to master. Now, this merge operation is actually pretty straightforward from Git's point of view, because if I go back to the previous slide, really all that has to happen for the merging of these 2 branches is just move master to now point at C5. It's what we refer to as a fast forward merge. There's nothing to it other than that, because there won't be any conflicts between, because C5 is a direct descendant of C3. There's nothing in between, or there's nothing over here. then merging these two branches is straightforward. This is what my this is what my repository now looks like. Okay, I've left head out, but head would be pointing at master because I did a git checkout of master here, so head would have to be pointing at that. So as I mentioned there, that's that particular merge is referred to as a fast forward, and a fast forward arises when the branch that's being merged into the master is directly upstream of the master, which it was in this case. Now, if you want to, you can delete a branch. Deleting a branch is nothing other than deleting the particular file associated with that branch name. That's all that delete means. We tend not to do. We tend to leave all the branches there if we do need to, for whatever reason, switch back to an earlier branch for whatever reason. Now we're still left with our feature branch though. And in this case, the merge is not as straightforward. So I'm saying here, frequently merging branches are diverging. Technically, bug Y and master, well, not technically, they were not diverging branches. One was directly upstream of the other. But more often than not, branches that you do want to merge are diverging. Always, though, diverging branches, they always share a common ancestor. If you look back far enough in the path of commits. But when you try and merge diverging branches, there can often be what we call conflicting changes. And Git can't resolve these conflicting changes, but it tells you where they are. Now, what I mean by that is if we look at our scenario here, it's quite likely that this C6 commit, it may have changes to files that were also modified in these two commits here. And so that's what we mean by conflicting changes. Clearly, Git doesn't know anything about source code, so it can't resolve those conflicts, but it will tell you where they occur in the actual files, and we'll see how it does that in a moment. The conflicts are when you've got edits to the same files on diverging branches. In terms of how I would do the merging of my feature branch, my feature expanse and master, same as before, git checkout master, because I'm always merging into the master, then git merge feature X. But now it's going to come back with some detail. The merging of the bug Y and master would have the response would have been fairly clean kind of response. But here it's going to tell me that there are some conflicts, and what it will do is it will tell you which particular files are the problem ones, and you can find out. I think it actually lists them here, even though I haven't done it. But if you do a git status, because remember now, when you do a git merge, what's actually happening is there are lots of changes happening to your working directory. Okay. Because it's essentially taking all of the commits that are on this feature X branch, all of the commits that master doesn't know about, which were, again, if I go back, these two, it takes these two snapshots and applies them to the working directory. So if I do a git status, and git status, remember, tells me about the status of my working directory. If I do a git status after essentially a failed merge or a partial merge, then when I do git status, you look for this kind of stuff here. It tells you that both branches modified a particular file, and it'll list all of the files that were modified by both branches that you're trying to merge. In addition, if you actually look inside these files, there are what are called conflict markers put into the file by Git for you. And this is how they will look in when you view them in the editor. And you will do this in one of the labs that I've set up for you. So when you scan down through a particular file that has conflicts, you'll find this marker. This is kind of the beginning of where the conflict is. It'll show you some code from, this is essentially the master. Then it'll say, here's the code that's in the other branch in the same part of the file. And you need to decide, should I use this code, or is it a mixture of both of them? And that's only resolved by collaboration with the various people that were involved in the development of the feature. Okay, so what we now have is in our working directory, we've got a couple of files that have these conflict markers in them, and we need to fix those files, if you like. So we need to edit the conflicting files. We need to make sure that we remove the markers from those conflicting files when we're happy that we know what the resolution is. Because as long as those conflict markers remain in the file, Git actually will go looking for them, and if it finds them, then it won't allow you to progress any further. So you've got to remove those conflict markers, and then you simply do a staging and committing as before. Git add -a, git commit. And when you do the commit, this maybe is what your repository will now look like. You now have a new commit, but this commit actually has two parents. Most commits have one parent. And so this is now, master is now pointing at this guy, head is pointing at that. Feature X is still pointing back here. That's okay. So this is how we merge diverging branches that have conflicts. We try and do the merge, but we'll get an error report back from Git. We then can just do a Git status on our working directory to find out what are the problematic files. Having found the problematic files in our working directory, we go through this procedure here of editing the conflicting files, get rid of the markers, do a staging and commit, and now you have successfully completed a merging of diverging conflicting branches, all of which I kind of set up for you in the lab anyway. Right, a lot of stuff going on there. So this whole branch edit merge workflow that I'm talking about. So you should always, I'm sorry, I'm saying here, you should rather than can't, you should never do editing and committing when the current branch is the master branch. Now, sometimes we just fall into that trap. Technically, it's fine, you're allowed to do it, but it's just bad practice, as I mentioned before. So always when you've got when you're doing any of these tasks, which I mentioned at the beginning, always the first step is create a branch of the master, do your development work on that branch, and then if it's appropriate, merge it back into the master. So you're always committing on branches other than the master branch. And you could have two branches going on at the same time that you're doing commits to, and you just have to keep switching back and forth between them, but you just got to manage all of that kind of yourselves. At least you're going to have one branch off of the master that you're going to be doing your development work on. But you could potentially, if you're trying to juggle two balls at the same time, fix a bug and develop a feature. Strictly speaking, they should be done on separate branches off of the master branch and merged back in at some stage. Maybe just too much talk now at this stage, so maybe I should let you do some lab work. So if we go back to, there's only 2 slides that I want to cover here, and this set of slides anyway, so maybe I'll let them go until next week. Excuse me. So if we go back to Moodle and we go to the lab exercises, you can work on that class exercise that I talked about there a while back. You can also work on this lab here. This will involve using that git cat file. You kind of have to navigate through a network of tree and blob tree objects to get to a particular file. And now I do have and when you've completed that lab, you can submit it. There's no submission required on this one. I do have a branching lab as well, which I think I can actually open up maybe now. I'll think about it as you're working your way through it. And if I do want to open it up, then you can work on it, but I'll reflect on it to see whether I should get you to do that or not. But certainly work on this exercise, work on this lab, submit that one, and I'll let you work away. Also, you will have noticed now that I've published the results for the last week's lab and the Mocha testing one as well. And if I just scroll up here, see, I have published a sample solution to the exercise at the end of the Mocha testing lab. Where did I put it? There, sample solution. You can just have a quick look at it. I just give you an implementation of the search method, if you remember. And I also show you the possible tests for my search method. In terms of how I marked, let's say, the Mocha lab, there were 10 marks for it. I gave 4 marks for having the full git log. I just ran a git log command on your repository. And if you had all of the commits that were prescribed in the lab, then you got 4 out of 4. I gave 4 marks for your implementation of tests for the search method. And I gave 2 marks for trying to follow the TDD process. And the way I checked whether you try to follow TDD or not is by looking at your git log. You should really have maybe 2, maybe 3, I'd say, commits associated with the development of the search method. Maybe the first commit was where the search method just worked with price searching. The second commit worked with searching for products that had a certain string in their name, and maybe the third commit would have been the exception handling or something like that. At least 2, possibly 3 commits. Then I would have said, look, you tried TDD at least. So 10 marks in total, 4 for following the commits that I gave you in the lab, 2 marks for trying to follow TDD, and 4 marks for how well you tested the search method. So I looked at your Mocha test for the search method. Okay, in terms of the second lab, then the last week's lab, that was a straightforward. I just did a git log of your repository, and if you had pretty much all of the commits, there was only 5 marks going for that lab, 10 marks for the Mocha one because it was slightly more challenging. 5 marks for last week's lab, and you just got 5 out of 5 if you had all of the commits or most of them anyway. You should really have all of them though. If you didn't get any mark, it's either because you didn't submit anything, or you didn't follow my instructions about configuring your local Git to have your name as it appears on Moodle. I did advise you to make sure you that you do configure your local Git before last week's lab. So pretty much everybody got 5 out of 5, or most people got 5 out of 5 for last week's lab though. Anyway, if you've got any queries, you can contact me on Slack about the results. Okay, I'll let you work on the 2 exercises, the 2 Git-related exercises for the remaining time. What time have we left? We've got a good bit. So I'll let you work away and contact me if you want to talk to me about anything.